Okay, let's talk a little bit more about power series so we can kind of finally do some Taylor series manipulation stuff. So just recall a power series is a series, so it's a summation from n equals 0 to infinity with c sub n as the coefficients, and I've got power series centered at a. I'll have an x minus a to the n like this. So if you recall from your algebra class, like f of x plus a shifts x to the left by a, right? So if I had a graph of f of x and I'd want to graph f of x plus a, it just shifts it to the left by a. This shifts subtraction by a, shifts it to the right by a. So what we're gonna just look at and prove things about c sub n x to the n from n equals 0 to infinity, and they'll work. The things that we prove will work for any power series. We're just going to shift them left and right to center them wherever we need to. But we'll just deal with them centered at 0 without loss of generality that way, and then we can shift them wherever we want. So our theorems are all just going to be stated with a power series that looks like c sub n x to the n rather than x minus a to the n. And then we'll deal with the ramifications of that for other things for the Taylor series centered at different points later, just by the shifting. Okay, so the first thing I want to do is I want to prove something about differentiation, right? If I have a function f of x and it's defined by this power series, so f of x is defined by c sub n x to the n from n equals 0 to infinity, then what would be really nice, it would be nice if when we differentiate, if f prime at x was equal to, well, if I differentiate a constant term when n equals 0, I get 0. So I'm going to n equals 1 to infinity, c sub n times n times x to the n minus 1. If I differentiate term by term and then add up those terms, it'd be nice if I got the right thing. And this is true as long as we stay within our radius of convergence up here. The radius of convergence down here will be the same. And in fact, we can say that if it's sort of absolutely continuous up there, it's absolutely convergent up here, then it's absolutely convergent down here, and so on. And so this does actually work out rather nicely. This correspondence works. So let's prove a theorem and write down the specifics about that. So here's the theorem. So let f of x be defined to be equal to the sum from 0 to infinity c sub n x to the n. And suppose the radius of convergence is r. So that for x in negative r to r, the series converges. Okay. Then for any epsilon bigger than 0, the series sum c sub n times n x to the n minus 1 from n equals 1 to infinity converges. uniformly on negative r plus epsilon, so a little bit to the right of negative r, and r minus epsilon a little bit to the left of r. So that's a slightly smaller interval than the open interval here, but it's closed. And I've got uniform convergence on that closed interval. And further, f is differentiable and has f prime at x equal to that sum that we want it to be from n equals 1 to infinity c sub n times x to the n minus 1. Okay, so this is kind of a big theorem. All I need is that f is defined as a power series. I don't need anything else. And the power series has a radius of convergence. So the radius has to be positive. It can't just be continuous, or it can't be just convergent at a point. I have to have r strictly bigger than 0. It could be infinity, but it just can't be 0. I can't just have convergent at a point. Other than that, we don't have very many restrictions at all. We just get the exact same thing for the derivative function. And this sort of shows how power series and Taylor series are going to be really nice for us. We can write the Taylor series for a function, and in its radius of convergence, differentiation works just fine. We also get sort of not really a corollary, but by the same proof, and so I'm not going to prove it twice, I'll prove this one, but we get by the same sort of style of proof that integration works just fine too. So let's just prove the differentiation, and then we'll write the statement for integration. So here's the proof of this. So we have to let epsilon be bigger than 0. Okay, and then for x in absolute value less than r minus epsilon, the sum c sub n x to the n in absolute value is less than or equal to the sum of c sub n r minus epsilon to the n in absolute value. Okay. But the right-hand side converges absolutely by the root test. So let's see that. Okay, so recall that if the radius of convergence is r, 1 over r would be the lim sup. So lim sup of the nth root of the absolute value of c sub n equals 1 over r. If we look at, and since it converges, this is less than 1. Yeah. If we look at the lim sup of the nth root of c sub n r minus epsilon to the n, that's equal to, well, I can pull out that r minus epsilon, so it's going to be r minus epsilon times 1 over r, which is also strictly less than 1, right? So it converges by the root test too. Okay. And in fact, I can move a little bit to the right and still have convergence. So what I'm going to do is I'm going to let m equal r minus epsilon over r plus 1 over 2. So let's see what's going on here. Here's 1. Here's 1 over r. Here's r minus epsilon over r. And I'm going to take this value halfway between these two things. And that's still going to be less than 1, so it's still going to converge by the root test in there. And I'm going to call it m so that I can use that Weierstrass m test, if you recall that from the other video. Okay, so since the absolute value of c sub n, r minus epsilon to the n, and the limit is eventually less than m, is eventually true for all n large enough. That's because the lim sup of this thing is strictly less than m. We get that the absolute value of c sub n r minus epsilon to the n is less than m to the n for all n large enough. Okay, and this is enough to say we have absolute convergence or uniform convergence by the Weierstrass m test. I think this was 710, I think. We have uniform convergence on r minus epsilon, negative r plus epsilon, and to r minus epsilon on that, using the Weierstrass m test. Okay, how that just shows uniform convergence of f on this interval. That doesn't have anything to do with the uniform convergence of the derivative, but let's just look at the same thing if I pull an n down from the derivative. So the absolute value of c sub n x to the n, if I take the nth root of that and I take the lim sup, that's going to have the same lim sup as the nth root of c sub n times x to the n minus 1. Okay, why is that? It's because the nth root of n goes to 1, right? So I can break this up into two pieces, and this would be the lim sup of c sub n in nth root, I don't have to have that in there, in absolute value times 1 times absolute value of x. So we have the same radius of convergence for both of these. Okay, now the theorem that we stated about derivatives and didn't prove was, let me recall that, if f sub n prime converges and f is continuous at some point where f sub n converges to f, then f sub n converges to f. F sub n prime converges to f prime uniformly on all these things. And that's exactly the case that we're in. F is continuous because we showed uniform convergence of polynomials. So those polynomials are all continuous. Uniform convergence of a continuous function is continuous, so we get this from uniform convergence of polynomials are continuous. Okay. This we showed by the Weierstrass-M test. And the continuity, that's part of this thing too, right? At some point. And so this checks out and we're done. That was our proof. So the entire part of that was showing that f sub n prime converges uniformly. Okay, so that's really nice for us, and the integration also holds. So let me just state that. If f sub x is defined to be equal to the sum of c sub n x to the n from n equals 0 to infinity, we can say that the integral of f sub x dx is equal to the integral of the sum of the c sub n's x to the n from n equals 0 to infinity dx, and then we get this plus some constant, right? That's sort of not there yet, but I'm gonna say why that's important. And instead of the sum and the integral, I can kind of switch these two things. So this is equal to, so the integral of f dx is equal to the sum. Well, I'm going to integrate these things term by term, and so I get x to the n plus 1 over n plus 1 c sub n, and these start at n equals 0 and go to infinity. So there's no constant term here, and then I'm just going to add in a plus c sub negative 1, where c sub negative 1 is defined by an initial condition on f of x equal to the integral from, say, a to x little f dx. Okay, so that's kind of the same thing as differentiation. I can differentiate term by term, or I can integrate term by term. Okay, so let's just see a simple example. Okay, say e to the x. We haven't proven anything about e to the x, and in the next video we're going to talk about why we define things this way. But let's just say e to the x is equal to the sum from n equals 0 to infinity. Well, I'm going to find the Taylor series at 0. E to the x has its derivative is the same thing for all of its derivatives, is just e to the x. So the Taylor polynomials that we come up with are going to be evaluated at 0, and that's going to be 1 is the nth derivative at 0 for all of the EDX's divided by n factorial. If you remember your Taylor polynomials, we're just not going to stop at any point, so these are going to go off to infinity. Okay, and let's take a derivative of this. So the derivative of e to the x should equal the derivative of the sum from n equals 0 to infinity of x to the n over n factorial, and by the theorem we just proved, that's the sum from n equals 0 to infinity of the derivatives of x to the n over n factorial. Well, at n equals 0, this is just a constant, so it's going to be 0. So this is the sum from n equals 1 to infinity of n x to the n minus 1 over n factorial. Well, n divided by n factorial just looks like, so 1 over n minus 1 factorial, so I get x to the n minus 1 over n minus 1 factorial. If I just change my integration, say m equals n plus 1, is that what I want to do for my index changing? Then m minus 1 equals n, right? So anytime I put a n in here, I see a m minus 1 equals 1. No, I think I want a minus sign here. So I want a minus 1, and that's going to make that a plus 1, and that's going to be a plus 1. Okay, and I'm just changing my index. So n minus 1 is m, and that's going to be an m factorial. So I haven't actually changed any of the values that I'm adding up. I'm just changing what the variable is. And I'm starting from m plus 1 equals 0. So m plus 1 equals 1, so that's the same thing as m equals 0 up to infinity on this x to the m over m factorial, which by definition was e to the x again, just with a different variable on the index. Okay, so if we define e to the x to be like this, its derivative turns out to be itself. And we can perform the same sort of thing with the integral. As long as we define e to the 0 to be 1, then that c sub negative 1 is a 1 that gets stuck on the beginning of this again, and everything works out fine. Okay, so in the next video we're going to explore this idea of how to define e to the x and natural log of x using these Taylor series.